Okay, great. So, bit loud for me. The microphone, speaker right there. So, yeah, I made a little late pattern of the course. So, the 4 lectures, as you know, and the goal was to start with the Ghate representation, reduce it mod P, and understand the structure. At the most basic level, if you don't know much about Ghate representations, these are 2-dimensional vector spaces with an action into a Ghate group. And at the very least, you can just try and remember this question: is the Ghate representation irreducible or reducible? So irreducible means that roughly, if you look at the matrices you get, 2 by 2 matrices, you get it full, and irreducible means, reducible means you get diagonal matrices, roughly. Okay? So reducible is a sparse set of matrices, and irreducible is not completely true, but those kinds of matrices. But more formally, direct sum of characters on P reduction. Direct sum of characters or irreducible representation, not a direct sum of characters. 1 plus 1 or 2. Whether you can write 2 as 2 or 1 plus 1. So that's the question. It's a very basic question. It's a yes-no type question. Is it reducible or reducible? Remarkably complicated question. It's like a fractal-like situation. Many, many beautiful patterns here. I'm working on this for many years in the crystalline world, the semi-stable world, which is new to me. So a lot of Vibhavori stuff is coming to the picture now. Anyway, so what are we trying to do? I already explained this bottom part, and today I'm going to explain these two, today and the next lecture, and then on the last lecture I'll explain this part. So what you do is, it's very hard to reduce the Ghate representation. So you go across to a Banach space, and then you reduce the Banach space, which is a lattice in the Banach space, and reduce it. And these are representations of GL2QP, these are representations of the Ghate group of QP. Okay? So you try and reduce this lattice, and you try and show, so you get something, and one knows that this diagram commutes because there's now a functor of Gomez which captures both of these directions. The mod P local Langlands correspondence actually maybe goes this way or that way, I don't know, but the 2 functions anyway of Gomez. But this is functorial, these maps are actually functorial, so this diagram commutes, right? If you have a morphism this way, then you get these things are functorial. So this diagram commutes, and so if you're trying to do this direction, you can try and go around here. This map is, and from this direction to that direction is injective. You know, the representation, there's a unique mod P GL2QP representation corresponding to it. So if you go around this way, you immediately know what the Ghate representation is. That's the idea of the course, but it's only going to come in lecture 4. Okay? So we did this, I've already mod P LLC. Mod P LLC is here, and these are the usual p-adic local Langlands correspondences. But to define the p-adic local Langlands correspondence, I'm going to do it only in one very particular setting. Actually, the crystalline setting is a little easier, and we've done it maybe just 10 minutes. But the semi-stable setting is a bit more involved. So it uses some p-adic functional analysis, just functional analysis of one variable. So not so hard, and let's not use fancy words like functional analysis. Basically, uses the notion of differentiability of a p-adic function of some kind. Okay, so there are some functions which are not k times differentiable, but r times differentiable, which are where r is k minus 2. Actually, r by 2 times differentiable, where r is k minus 2. So we have to understand what it means to be differentiable today. And before we can begin to even talk about this Banach space next time. Okay, these are some collection of differentiable functions. So today it's kind of like so actually we're running a 1-semester seminar in TIFR, going through Gomez's paper every Friday. And it takes some time, there's 40-50 pages in that thing. Today I'm going to give a very superficial overview of the first half of that paper. The first half is about continuity and differentiability, and the second half is about distributions on continuous functions, differentiable functions, which we don't need for the Banach space. So I did try and work out all the proofs ourselves with some people at TIFR help and write them down in the notes. It's 23 pages, and I noticed I'm doing 3 pages a lecture. So we circulated this morning, but all the complete proofs are there, right? With all small details. The handwriting is not great, but if you just stare at it a little bit, you'll find the details. Okay. So this lecture might be a little superficial and notational, new proofs, but I strongly encourage you, if you're interested, to look at one or two of those proofs. Maybe I'll do one or two easy ones. Let's see. Okay. So p-adic Banach spaces. I think there's a bit of crackle still. Move this down. Yeah. So some notation. VP is a valuation from CP. It's the p-adic valuation taking P to 1. You won't write that. Usual notation, you need some p-adic number field. So for some parts of this lecture, E can be an arbitrary subfield of CP. This is p-adic complex numbers, by the way. You take QP, you take QP bar, and then you complete with respect to p-adic complex numbers. So E is a finite extension of QP, often, but it can be an arbitrary field, an extension of QP or something like that for some parts of this lecture, but very soon it will be a finite extension of QP. So this is a subfield. And then you have the usual things which I won't write down because they've come up many times. OE is the ring of integers. This is valuation greater than 0. Then you have the maximal ideal, ME, which is going to be generated by a uniformizer if it's discrete, by E, and the residue field KE, which is OE by ME. Right, so these are the basic notations. Okay, so let's define a p-adic Banach space first. So let B be an E vector space. So there's a topological vector space, but the topology is defined by valuation. So let's just recall quickly the definition of valuation. Even though I wrote BP up there, you might have seen this valuation in books, textbooks on number theory, but maybe on vector spaces it's a very similar definition. So let's just do it. So evaluation VB, valuation on B, is a function VB from B to R union infinity, such that three conditions hold. VB of x is 0. This is the usual condition. The only time the valuation is 0 is if x is 0. 2, a triangular inequality on Archimedean is greater than or equal to. Okay, so Converse uses the word infimum, and I sometimes use the word minimum, so that might, yeah.
Sir,
yeah.
Infinity.
Sorry?
Valuation is infinity.
Valuation.
The first line of definition.
B be an E vector space. A valuation on B is a function, yeah.
No.
The first condition
Yes.
of valuation.
VBX is infinity if you not.
Sorry. It's infinity, yes. Infinity if only if x is 0. And the valuation of x plus y is greater than the infimum of valuation of x and valuation of y. So this is always true. It's actually wrong in my notes. So you guys, tutors were supposed to look at typos. Yeah. Anyway. And third thing is the valuation of lambda x is equal to the valuation of lambda plus the valuation of x. So this is for lambda, this is for xy belonging to B, this is for x belonging to B, and this is for lambda in E and x in E. Okay, so that looks very much like a value. If you take B to be E, that's the usual definition of valuation, right? This, yeah. Okay, great. So what is a Banach space? So an E Banach. Did I say E Banach? Did I say, yeah, so this, E vector space. Right, so B is an E vector space. An E Banach space B is a topological vector space of this over E with topology given by a valuation PB for which it is complete. Okay, so just a topological vector space, but as you, I hope you know, may not know if you're very young, but Banach spaces are complete. Right? That's the whole point of Banach spaces. They're complete with respect to symmetry. So here, there's a valuation. There's also a notion of norm. Notion of norm is like p to the minus of the valuation, right? So that gives you a distance, and with respect to that distance function, it should be complete. So Gomez adopts this philosophy never to write a norm on any of those 50 pages. It's always valuation. So you have to pick a convention. So writing norms everywhere, he writes valuations everywhere. One's additive notation, one's multiplicative notation. And so choose one of those conventions. So a map, sometimes you shorten this to E Banach instead of saying E Banach space. So a map, or morphism, I think he calls it morphism, so let me just say map, make it less scary. F between V1 and V2, these are E Banachs, is just a continuous linear map. Banachs is a continuous linear map. This is what a morphism or map is. And finally, this word comes up a little bit, isometry. So an isometry is just a map which is also preserving the distance. A map F from B1 to B2 is an isometry. If BB2 of f of x is equal to BB1 of x, or x belongs to B1. So the valuation is preserved. You move across. Yeah. Sorry? No, not subjective, just a linear map. Continuous linear map. So continue the topologies on both sides, so at the very least you expect its vector spaces, so both the structures also. Topology is preserved, and I mean, something to do with the topology, and it's also something to do with the vector space structure. No, I don't think so. Okay, so here are some examples. So these examples look very particular, but in some sense I think they're very general. Okay, so let I be a set. Usually the set is going to be the French natural numbers. So French natural numbers contain, they contain 0, right? So that's, everywhere 0 is needed. So just remember, I won't write it, but natural numbers here contain 0. So Gomez, for a while, he tries to be quite general and let I be an arbitrary subset, and then when he says convergence, he says tends to 0 in the filter of complements of finite sets and things like that. Some fancy words like that. But we will just assume that you have usual sequences and usual convergence of sequences and things like that. But if you want to be a bit more general, then you can take this to an arbitrary set. Okay, so what are the main examples? The first one is what's called L infinity, lower L infinity, i.e. Oh, one more thing. So I should have said that at the beginning, those notes are in French and this is in English. So at the very least, you can give me credit for doing that much. Maybe I've not added anything to the mathematics, but it's a conversion from French to English. So at least that step, which is 50% of the work, I think, has been done. But also lots of details that you picked up in the proofs and some typos that you corrected. I'm sure I've introduced new ones, but some of the formulas are a bit off, some of the algebra formulas are a bit off. So those things have been as much as possible corrected. But two big things that are changed between the notes and this is that the p-adic field everywhere is L, capital L there, but it's E here. That's because in this paper CG, which I just erased, the p-adic field is E. So I just want the lectures to be consistent. That's one thing. And the second thing is all these functions are called phi. And here the functions are called little g, because that's the notation used for functions for some reason in our paper. Okay, so those are the two main things you should watch out, and sometimes I might write a phi instead of g and L instead of E. So just correct me. So here I remember to write E. So these are sequences AI such that, okay, maybe I'll write the norm just for once, AIP, which is p to the minus EP AI, these are bounded. Okay, the infinity means there that these numbers, the norms are bounded from above, or the valuations are bounded from below. Okay? So it's all sequences of the valuation is greater than or equal to 10, for instance. That would be an example of an element of this. But the bound is independent, but I mean, no, sorry, yeah. The bound may depend on the sequence, of course. Okay, so that's one. Yeah. So what is the valuation which makes this a Banach space? So B L infinity is the name of the valuation. B sub L infinity of AI. This is just the infimum, the smallest valuation you have of the sequence. Okay, take the minimum of all the valuations to check that this is a valuation indeed and that this is complete. Okay, so bounded sequences. There's a slightly more interesting, a very important example, which is a sub-Banach space of this Banach space. And that consists of all sequences with what property? Can someone guess what I'm erasing?
Convergent.
All sequences, yes, convergent, I mean going to zero. Okay, where the terms go to zero. So that's another very important example. So there's L infinity 0, i.e., which is all sequences, subspace of L infinity, i.e., consisting of all sequences, AI, such that so this is where I was saying there's a bit of issue about what it means for convergence for an arbitrary set, right? So there's some fancy notion of convergence for an arbitrary set. But let's forget about that. Just think of I as the natural numbers, and this is the usual convergence of the sequence. Mark. This is the closure. So there's another natural set of subset of sequences, a vector space of subspace of sequences in here, namely all the sequences which have only finitely many non-zero terms, right? They always converge to zero, right? But that's not complete because you can take longer and longer tails and right, or something. But this is the closure of the finite dimension, sorry, the subspace of sequences having only a finite number of terms non-zero. Right, because those sequences anyway are tending to zero, so in the large they anyway look like zero more or less in terms. Closer and closer to them by proximity, by finite heads of the sequence. Okay, now there's a proposition here which I think I may not use much, but it may be used in some of the proofs, so let me read it out loud. So there's the open mapping theorem. So Gomez makes this nice remark that many of the theorems in p-adic Banach spaces are easier than in real Banach spaces. Okay? So life is easier. It's more like Hilbert space theory, which Hilbert spaces have more structure. There's a inner product, etc. Right? So a bit more structure, and then there are more things that are true orthonormal bases and things like that. But here in this p-adic world, somehow you already have orthonormal bases and things, even without putting any Hilbert space structure. Okay, so there's just a remark that he makes, so let me make that remark. And then he states a few theorems which he uses sometimes in the proof. I won't write them down, it'll take some time. If you have the notes that were circulated if you open your phones, the notes were circulated this morning. But, so the first statement is the open mapping theorem. It says, I'll read it out, you can guess what it is. That if you have a map of E-Banach spaces, F from B1 to B2, which is bijective, so the inverse, so it's a continuous linear map, but the inverse exists as a vector space map, then the inverse map is continuous. Right? In other words, it's an open map. So that's one statement. It's used one or two places. And the second thing is that something called the Banach-Steinhaus theorem. It says that if you have a sequence of continuous maps, linear continuous maps, or just maps as we call them here. So a limit of linear continuous maps between Banach spaces is also continuous. This is also a statement that's called the Banach-Steinhaus theorem and may be used or may not be used. So let me not spend too much time on those things. I'm going to skip some proofs. Okay, so there's a very nice article of Serre in IHES in 1967 in the Institut des Hautes Scientifiques journal, a very fancy journal, where he developed much of this theory. I think it's 1967, I might be wrong. There's a graduate student who's translated that paper into English, and I highly recommend you read that as a first introduction to some of these things. It's almost like an undergraduate, BSRP lecture, that paper. It's so clear. Okay, so section 1 was that. I think I'll move to section 2. I'm also going to follow the numbering in Gomez's paper, which is here. Take a look so that you can quickly refer to the French version if you need to. So I might skip some numbers, but okay, orthonormal basis of Banach spaces. P-adic Banach spaces. Whenever I write Banach, I mean in E-Banach in the sense in the previous section. So definition. Orthonormal basis. What is this? A family of elements, EI. Elements of B, E-Banach B. Is called an orthonormal basis of B. Orthonormal basis of B if the map. So first of all, these things should span B, but spanning is not here in the sense of finite linear combinations. You can have infinitely many coefficients, non-zero. That's a little bit different from what you're used to. So he says it in a fancier way. Let me say the fancier way first and then translate to the less fancy way. If the map from L infinity 0 IE B given by taking a sequence AI to a summation AI e to the I is an isometry, a symmetry of E Banach. Yeah, right, E Banach spaces one last time, shortened to Banach at some point. So more concretely, you can write every element in this form. Every x in B has an expansion, summation AI, EI. So there exists AI in E with AI tending to 0. It's almost like they're finitely many, but not quite, but at least they're tending to 0. Right? AI tending to 0 means the norm tends to 0 or the valuation tends to infinity. Right? Many ways to write the same, 3 ways to write the same thing. So that's one condition, and the second is the isometry condition. So if you look at, just translating above, the valuation of x is just the, has to be, the valuation of both sides has to be the same. It's just the infimum of these things. Okay, so this is the most important thing that one hunts for whenever you have a p-adic Banach space. You try and look for orthonormal bases. And of course, they're not unique. It's the same Banach spaces may have 2 different orthonormal bases. And much of the flavor of the first 20-30 pages of those notes, which is all the things, all that I'm summarizing here, is to hunt for various interesting kinds of orthonormal bases. Okay? So we'll see many examples by the way. Okay, so there's a weaker notion. So this is called an orthonormal basis. There's a weaker notion of a Banach basis, which is looks a bit more natural, and often it's hard to find an orthonormal basis. You can only find a Banach basis. So that's almost an orthonormal basis, but not quite. So let me explain how, why. So here somehow the distances and everything match completely, right? Topologies match completely, but in the Banach basis, the topologies evaluation doesn't quite match with this evaluation, but almost does, up to some finite error or some bounded error. Okay, so more precisely, so there's 2 parts to the definition. Let me put a bullet point here. Another bullet point is over here. So the second part is that a family, I won't write those words again. EI is a Banach basis or only a Banach basis, to say that it's a little less strong. A Banach basis of B, not an orthonormal basis, but a Banach basis of B. If, of course, it spans it, but this map here is not an isometry, but just an isomorphism. Okay, so the topologies are compatible on both sides, but the actual distances are not compatible. Okay? If the map above at the top of the board, map star is only again an isomorphism. Banach spaces. So I think I'm going to squeeze this in. This is equivalent to, did I number these? 1 and 2? Yeah. 1 plus 2 prime. So 1 has to hold because it still spans it, but 2 is a bit different, and that is that there exists a C, I'm going to put it over here, sorry, because it comes naturally here. C greater than 0, I hope you can read this, such that the valuation of any element x is not equal to the infimum of the valuations of the AIs, but is squeezed between numbers. Hope you can read that. So the valuation of x, p-adic valuation of x is squeezed between the infimum of the valuations of AIs minus c plus the valuations and c plus the infimum of the valuations of the AIs. It's not exactly equal to it. If c is equal to 0, it will be an isometry, right? But it's bounded between these two quantities. So topologies are compatible, but not with this thing. Okay, so here are some examples, and of an OND. Well, here, I guess the obvious one. So in L infinity 0, can anyone guess an orthonormal basis? Let's do a little example. So delta is a sequence which is 0 everywhere but 1 at the ith place. Right? This is a sequence which converges to 0. Right? And certainly you can write any element of that as a linear combination of these things. So these will form an orthonormal basis. Then connection of delta i's form an OND. I have to check the two conditions, but mentally check them when I'm writing. Almost by definition. Okay, so now here's the main proposition of the subject, which I think one should not proceed without sort of understanding the proof of it, but if I do the proof, then the whole 1.5 hours will go on that. But it's in Sayre's article, and I think it's copied into. And the Sayre's article is also a good article to read if you want to understand Coleman theory, Ghate families of modular forms. For those of you who want to understand what modular forms, the whole language is in this language of Ghate compact space, compact operators, etc. That's the whole point of that article. But we're just using the beginning part. Yes.
If we have a given line basis, is it possible to get orthonormal basis?
It may not be an orthonormal basis. It may be.
But is it possible to get some
Modified in some way? Good question. Yes. Yes. So you're sort of bounded between things. So yeah, I have to think about that. That's a real technical question. I don't know exactly. It's like, you know, if you have a bunch of EIs, which is orthonormal basis, and you divide everything by, you multiply some things by P and you divide some things by P, right? So that the power of P that you multiply the things by, those are bounded. Then that will not be maybe a Banach basis, orthonormal basis, I'm not sure, but it will be a Banach basis. I don't know, this, yeah.
VB may not take the same values as VP, right? VB may not take the same values as VP. So if VB is something strange like that, you may not be able to modify the basis.
Okay, yeah, I have to think that. I'm not completely sure. But certainly this is a weaker notion, and in some cases in Coleman he only constructs a Banach basis but not an orthonormal basis. So yeah, maybe there is some jump to go from one to the other. Okay, so proposition 1.5 in Coleman. So now say that E is discrete. A finite extension of P. Let's think of that, but more precise, a little bit more generally, E is a discrete. E is of discrete valuation. Translate over French. And phi E, we already wrote this, is the uniformizer. Then the following statements are true. 1. Every E Banach has a Banach basis. And 2, it possesses, an E Banach possesses an orthonormal basis. I guess this answers your question a little bit, right? Because I think this is what he was saying. They may not even have an E Banach space. There's an F and only condition here. So I was wrong to say you can just modify it. Sometimes you can't make it. So an E Banach B has an orthonormal basis if and only if the value groups of B and E are the same. Okay, so there's a necessary insufficient condition to have a Banach orthonormal basis. But you always have a Banach basis, you may not have an orthonormal basis. Okay, so here is, and there's something even nicer. So moreover, EIs form an ONB if and only if the reductions, so okay, I think I need these to belong to the unit ball. So these belong to what is called B0, which is the set of elements X such that PB of X is greater than or equal to 0. Take a bunch of elements which have valuation non-negative. Right, so these elements form an orthonormal basis. You can reduce them mod by E. Right, if and only if the reductions EI bar form a usual basis or an algebraic basis to distinguish it from an orthonormal basis, an algebraic basis of K, algebraic basis of B bar which is B0 modulo pi E. Algebraic basis of V bar over KE. KE, remember, was OE mod by E. So when do a collection of elements form an orthonormal basis? That happens exactly, I mean, they have to be elements so that you can reduce them mod P, but you have a bunch of elements, non-negative valuation, they form an ONB. If only if you take the reductions, that means you look at the quotients here, the vector space over OE mod by E, right? This is stable under OE by that third condition, right? In the definition of valuation, lambda times X is valuation lambda, right? So if the valuation of lambda and the valuation of X are both greater than or equal to 0, then the valuation of lambda X is greater than or equal to 0, right? So this is an OE module, B0. You go modulo pi E, B0, that's a vector space over OE mod K. OE mod pi E, which is KE. And then you have a usual notion of, because you have a field there, right? You have a field here too, but you have a field with no real topology, it's just a discrete object, OE mod pi E, and that should form a usual basis of this. So this is a condition. Nothing is not here, but I made him suffer through the proof of this 5-7 years ago. I think you guys should do the proof of this. It's actually 2-3 pages in my notes. I'm going to skip it now, but it's very important. Very important. So to answer your question, it's both yes and no. No formally, but yes informally, because this condition is often true for most of the valuations that we look at. So it will have an orthonormal basis also. Okay, so let's move on to some examples of Banach spaces and their orthonormal bases. I think before I do that, I want to talk about the dual of a Banach space, because it turns out that even though L infinity and L infinity 0 look like different Banach spaces, they're actually duals. One is the dual of the other. By the way, double duals are not isomorphic to the original things. Word called reflexive, which is not in the notes. At least one is the dual of the other. get it right, which is the dual of what equals sense. So write that down. So section 3, duals. Dual of an E1 now. This is strongly recommend you do this. This illustrates the theory very well. There's some trick in the proof which is quite important.
So using 2, you can give an ordinate definition of
Yes.
existence of
Using 2, yeah, that's true.
Yeah. If it is the inverse limit of B0.5.
Yes. Sorry, say it again.
Means you can
You
say
define it to be an OMB if this condition holds. That's what you're saying.
No. Orthonormal basis exists some ring B0 with that property, and B is actually inverse limit of B0 mod pi e to power n.
Yes.
If you can write that, it is equivalently saying that you have.
Okay. Okay. So dual of an E-Bana. So if B is an E-Bana, then I want to define B star, the dual. So it's what you think it is. It's the vector space of linear forms. I don't really need this for the course, but just to relate some object people already studied. It's the vector space of linear forms, linear maps from B to E. So continuous linear maps, right, like this, from B to E, but the second space is E, so called linear forms. With the strong topology, defined by the valuation. So here's the valuation of the dual. B star of a linear function. This is the same thing that you do in, the last time I used this was in my studying for my first year real analysis exam or complex real analysis exam as a graduate student 30 years ago. I managed to use this definition since then. But it's the same definition. You just take the infimum. It's funny how these things come back into your lives. All the story is in mathematics trying to understand everything in all your courses. There's also a lot of discrete math in this course. The derivative here is a difference operator, for instance. So you might think, oh no, I'm a very fancy mathematician, I'm doing discrete things. Right? So it's all over the place in a second. So yeah, it's the valuation of this minus the valuation of x. I was using the first year analysis definition, but here we're doing additive things, so I have to subtract and divide. And this should be this.
The second one is VBX.
VBX, thank you. You might have seen this definition, right? If you have an operator T, the norm of the operator T is you take T of x over x, right? You take the soup over all x belonging to some x not equal to 0, but not divided by 0. That's the norm of T. Something like that. Okay, so that's multiplicative notation and this is additive notation. So why strong topology? Because the weak topology is something, you say that you define it by convergence of sequences. So Fn converges to F if and only if Fn x converges to f of x, pointwise convergence. So then you can define what it means for Fn to converge to x. That's another definition of convergence. And apparently that's not good. So let me not get into it. I'll say a few words. By the Banach-Steinhaus theorem, it turns out that B star is still complete in the weak topology, but there's no valuation defining that topology. I do not approve something doesn't exist, but that's a remark in quotes. Except if it's finite dimensional, but in other cases there's no valuation which defines the topology. So weak topology is not a good definition, you take this strong topology. Okay, so here is one of the lemmas about this. So, 1, I is a set. 1. B is, if you have two sequences, B, I and AI, the first one is bounded. The second one is, I think they're called null sequences in SER, converging to 0. First one is just bounded, the second one converges to 0. Then, clearly this sequence, summation AI, BI, converges. Right, because the terms there, one of the sequences bounded, let's say by 10, and the other sequence is converging to 0. So those individual terms, AI, BI, will also converge to 0, and therefore the series converges. In the p-adic world, convergence is very easy, right? You just have to check whether the nth term goes to 0. Okay, so that's one remark. I hope I can squeeze the other one here, and that is that if you define the series by FB, so let's call this as FB of A. Maybe I can do it here. Cheat a bit and call this F lower B of A. I will write the whole definition again. So if FB of A is that series, summation AIBI, then the map, which takes B to FB, induces an isometry from L infinity to L infinity non-dual. The map B goes to FB, induces isometry in the US, you have to put a bit more accent on the O. Isometry from L infinity to L infinity 0 2. Not gonna make it. Try again. Read that. It says L infinity to L infinity 0 star. Right? Because FB is a functional, right? It's a linear map. So you have a natural map which takes a sequence B to FB, that series. It's a function on L infinity 0, right? That thing converges. So that map is in isometry. I said isometry, right? Okay, so there's a little check. And again, I think I won't have time for that. So the two Banach spaces that we came up are related. One is the dual of the other. Okay, great. So we've come up with some Banach spaces. Now let's get to some more interesting Banach spaces. So we have sequences and null sequences. Let's now talk about continuous functions. There's also a form of Banach space. And there's a very famous orthonormal basis there consisting of some binomial coefficients. So it's continuous functions on ZP taking values in E. Okay, so let's get to that example. Okay, so some notation. It's called C0. C0 CP E. C0 CP comma E. Space of all functions G. This is where I have to remember not to write phi. From ZP to E, which are continuous. ZP has its own topology, E has its own topology, same topology, p-adic topology. right? These functions should be continuous. Okay, so how is this a Banach space? Well, one has to check something, and here is the valuation. It's the soup node. So the valuation of a function, continuous function, is just the infimum x belonging to Zp of the values of the function. Enough brackets. G of Zp is compact, right? G of Zp is a compact set, right? So this supremum is there, and this is the valuation analog of that, infimum of these numbers, some proper number, some finite number. So this apparently makes C0 into an E-Banach space. Okay, so this is another example of a Banach space, an E-Banach, and let's try and now write down an orthonormal basis, a very famous orthonormal basis. So this is where the number theory comes in. So n is the set of natural numbers. And maybe we won't define too much notation here because for number theorists it's already standard. Everybody knows the definition of x choose n, right? If x is an integer, you know the definition of x choose n. If x is a variable, then it's x times x minus 1 times n times x minus n plus 1 divided by n factorial, right? It's the binomial polynomial. Think of x now as a variable, the same definition. So let me not waste time and write that down. Again, let me read some things out. So I'm claiming that since this is a function on Zp is a polynomial, so you can plug in anything into x. I'm claiming that the C0 adic valuation of the binomial coefficient is 0. Okay, it's a unit. Let's talk about that. So what do you notice about these binomial coefficients? They certainly take integers to integers, right? So if m is greater than or equal to n, then it's just a binomial coefficient, so it's an integer. M is less than n, you define it to be 0, there's some conventions, right? Anyway, it's always an integer from z to z, and it's a polynomial function, so it's continuous in the p-adic topology. So if you have, so that means it extends from a function from Zp to Zp, right? It's not clear that it takes Zp into, because it's a dividing by n factorial, but if you have an element of Zp, you can write it as a limit, p-adic limit of integers. We have continuity, it will converge to something in the closure of z on the other side, but that's Zp, right? So we will take Zp to Zp. So therefore, if you want to take the infimums here, we always know that these numbers are going to be greater than g is x choose n. We know that these numbers, valuation of g of x, are always greater than or equal to 0, right? Because it's taking Zp to Zp, so the infimum is at least greater than or equal to 0. That much we proved. So all you have to show is that you hit 0 at one point. What's a natural point? To make sure that x choose n hits valuation 0. We take x to be n, for instance, n choose n is 1, and the valuation of that particular variable function is 0. So it actually hits 0 at one point. Hits 1 at one point, and the valuation hits 0. So therefore the infimum is 0. Alright, so proposition, won't write the proof, take some time. Easy. The C0 adic valuation of x choose n is equal to 0. Because of that, this section has become very short. Move to section 2. So these numbers here, so Kolmes has a nested sequence of 3 numbers. I'm in chapter 1, so I'm not writing chapter 1 every time. But there's these 2 round brackets, which are sections inside the chapter. And then there's section sign, symbol for section, which are the subsections inside that particular section. Round brackets is 2 and section sign is subsection. So yeah, section 2, molar coefficients, Mahler's theorem. This is the first big theorem so far. The other one was a big theorem, was an abstract theorem of Banach spaces. This is sort of a very classical, famous theorem. Always gives a proof here, but it's a bit terse. There's a nice proof in Peter's book and many other places, I'm sure. Keith Conrad has some notes on the internet, for instance. Keith Conrad has notes for everything. But this also, and yeah, I think Peter's write-up is very good actually. I haven't read it for 10-15 years, but I once gave a course on that. So you can look there also. But the sketch of proof I've given in the notes here is following Pullman's. So the order in which you say things is very important. Anyway, Mahler coefficients of continuous functions. Okay, so definition. So G is a continuous function or any function. So what is this difference operator GK? It's defined by, so G of 0 is just G, 0 derivative. G of 1 is, who knows this? Computer science people in computer science classes. Forward difference operator. G of x plus 1 minus G of x, right? And then by recursion, you define, or induction, I don't know what the right word is, G of n plus 1 to be Gn of x plus 1 minus Gn of x. Right? G2 is, you do the same thing, but for G1. So it's just a discrete operation. You're just taking two values of the function at two different points and subtracting, but it gets one more complicated as you does this one more time. And then the Mahler coefficient of G is a continuous function. I should have said that somewhere. It's just the value of this derivative, discrete derivative, at 0. Okay? Some identities that these Mahler coefficients satisfy. Maybe I won't write them down. So there are two combinatorial entities. Let me read out one of them. So it says that you can write A and G in terms of the values of the function G. So there's another way to write the nth Mahler coefficient, which may be a definition. It's the sum from I equals 0 to n, the nth Mahler coefficient of G, is the sum from I equals 0 to n, minus 1 to the I, n choose I, G of n minus I. Okay, so there's a formula which writes the Mahler coefficients in terms of the values of the function, which you can try and prove. It's not so hard to do. For example, if you specialize that at n equals 1, you get something. G1 of 0, which should be G of 1 minus G of 0, right? And that's what that formula will give, G of 1 minus G of 0. There's another nice fact about these difference operators. If you take the kth derivative in this sense, discrete derivative, of the nth binomial coefficient, you get the n minus kth binomial coefficient. Nth binomial polynomial, you get the n minus kth binomial polynomial. So if you take the derivative, kth derivative of x choose n, you wind up with x choose n minus k. These are some easy facts. Okay, but the main point here of these Mahler coefficients is the following theorem. 2.3 says that if G is in C0, CPE, then two things. One, the limit as n tends to infinity of the an, or an tends to 0, I should just say that, is equal to 0. That's one thing. the Marlow coefficients actually in norm go to 0 and valuation go to infinity. And the second thing is that every function has a Marlow expansion. In other words, if you look at this series, which is it's like a formal object right now, make sense of it. So you can recover g of x from its Marlow coefficients in terms of this series expansion for all x belonging to Zp. So that series converges, first of all, for all x, and it converges to g of x. That's the importance of the Marlow coefficients. So Rindam reminded me a week or two ago, this is the p-adic analog of the Stone-Weierstrass theorem, because they are polynomials, right? Zp is a compact set. Polynomials, functions are dense, right, in continuous functions. Stone-Weierstrass theorem is something like that. You have binomial polynomials, and you can write every continuous function as a linear combination of these binomial polynomials. So the second part is the map C0 to ABE to infinity 0. Yeah, here maybe I take I as n, or maybe I have to. So you take g to its Marlow coefficients. And this is an isometry. Okay, so some things you have to check, because the valuation on one side is given as the sup norm, the valuation on the other side, or the infimum norm, right? The valuation on the other side is just the infimum of the valuation of the Marlow coefficients, right? So somehow those two things give the same valuation. One has to check that. So this is the content of this theorem. Again, it's 2-3 pages in my 1 or 2 pages in the notes. The order in which you do things is important, and there is no avoiding a particular technical lemma, which is highlighted on page 20, I think, lemma 1.5. Some number theory lemma which tells you about some valuations of some derivatives. But it's all, classical number theory, valuations of binomial coefficients and things. You know that P choose I has valuation 0 if I is 0 and P, but if I is strictly between 0 and P, and P 1 and P minus equal to 1 or 2P minus 1, then that is divisible by P, right? So these kinds of things, valuations of binomial coefficients, play a role in that. So there's a little bit of work, you can't get this for free, but anyway, so this is the statement. So now there's an immediate corollary of this, which I should have probably stated now because I'm not doing the proof. So corollary 2.4. If this is an isometry in terms of all the things we've been doing so far, what does this say about the binomial polynomials? It's an orthonormal basis, right? So corollary is that the x choose n, if n equals 0 log, form an ONB. Okay. This is proof, so I'll skip it. Oh, great. Again, lots of pages. We're skipping the 4 pages. All right, now there are a few more minor sections here, but I think to keep time in mind, I will not look at them so closely. I want to get to the main point, which are these differentiable functions, CR type. So we've just done C0. Let me make a picture of what else is in the notes in the next 5 pages. So there's some other spaces. There's C0, ZP, E. And there are also locally constant functions, LC, ZP, E. So locally constant just means that the function is locally constant, right? You can break ZP into some finitely many balls, right? H balls, radius p to the h or something, or whatever. A plus p to the h ZP, those balls. And on each of those A plus p to the h ZP, the function takes one value. Right? So that's locally constant, but h is arbitrary. So you take the union of all such things, you have locally constant function. It turns out, because every continuous function is uniformly continuous, ZP is compact, you can actually approximate any such function by a locally constant function. There's a little lemma and exercise. I was going to do it, but 20 minutes left, and I want to get a differentiability. Not spend too much time on continuity. Inside these spaces, so you may think for an algebraist like me, what the fuss is all about, because you have all these infinitely many spaces between this, and each one has their own theorems, etc. But this one is dense in that. So there's not so much action going on here, right? They're almost the same space, but each one has a slightly different orthonormal basis and things. It's a little subtle, the subject, but that's analysis for you. Okay, so yeah, so I won't talk about this, but there's also some orthonormal bases of locally constant functions in the notes. One of them are given by some sort of wave functions, a nice word in French. It has 2 words called ondelet and agulette or something.
Vaguelette.
I looked them up. Huh?
Vaguelette, right?
Vaguelette. Ondelet and vaguelette, and Google translates both of them as waves. So somehow the sizes of the balls that you take don't have to be constant when you're approximating continuous function. You can take balls of different sizes. So it's some of amplitudes, etc. Different, maybe wavelengths, I don't know, whatever. Some analogy with physics there. And so he has various orthonormal bases here of wave functions. That's one basis, orthonormal basis, which is on page 22 of my notes. And yeah, the coefficients there are called the amplitude coefficients. And there's another orthonormal basis, I think. Yeah, okay, anyway. Yeah, there's some exponential functions which also form a basis of the local constant functions. Take roots of unity, zeta to the power of x, where zeta is a p power root of unity, then they also form a basis of x is equal to. That's another result, but we don't really need it. So let's move on a little bit. So there's a new section here now, which I also am going to skip, called locally analytic functions. This is dense. It's one of the results. So locally analytic means, what do you think locally analytic means? A function from, it's a sub Banach space of this Banach space. And analytic in complex analysis means that you have a power series expansion, right, in Z. So here too, it's the same thing, or even in real analysis maybe. So inside here, you say that a function is locally analytic if, or H locally analytic if on H balls, on each of the H balls, finite H, you have a power series expansion. Okay, so there's a notion of locally analytic here. And there are many results about this. It's a Banach space and the various kinds of orthonormal bases here too. H ball means on A plus P to the 8 ZP. That's an open set inside ZP, where A belongs to ZP. But there's many overlaps. Any two balls are either equal or are disjoint. So it's a finite decomposition of ZP into some P to the H balls, as A varies between 0 and P to the H minus 1 on those balls. I'm saying H balls because the radius is not H exactly, right? I'm taking some long plus whatever. Yes. So there's a notion of a locally analytic function also, which is natural, but we don't really need it. This was supposed to be a survey to motivate some of these Banach spaces that are occurring in Gomez's paper and finally in Roy's work. I think I wanted to say something about one particular orthonormal basis, but I am missing that page. Okay, anyway. Yeah, there it is. There's a very, very interesting orthonormal basis for locally analytic functions, LAH. You put an H here, you mean locally analytic on each H ball. And it's given by x choose n, but there's a fudge factor in front. So here, all of these are continuous functions. So basically, to give an orthonormal basis, you basically modify this kind of thing, and you put some new coefficients here. So the orthonormal basis for locally analytic functions is x choose n, but in front of this you put a floor of n over p to the h factorial. So if you put a floor of n over p to the h factorial, you have to divide this by n over p to the h factorial. Very number theoretic condition. And you can unwind what that means. That going to 0 means limit for the valuation of a and g divided by n is positive. So yeah, I won't have time to state that unfortunately, but that's on page 23 of the notes, a very interesting orthonormal basis of this. Maybe I'll just write it here. There's an h to it, this has no h in it, it's a union over all h's. N over p to the h factorial x choose n. So this is the basis of O and E of L A H Z E E. Okay, so finally the last 22 minutes. 22 minutes, right? No, 17 minutes. Last 17 minutes, I can now try and talk about functions of differentiability, functions of class CR. So yeah, I was making this diagram. So these are locally constant. They have, of course, the best kinds of functions, simplest kinds of functions. Next is these power series expansion functions. Right? They have power series expansions everywhere, locally analytic functions. But we want a slightly, so we want something called CR ZPE, sitting inside C0 ZPE. Let me make that a little cleaner. Okay, so this is an R, it's supposed to be an R, where R is an integer, but it can be a rational number or a real number. So for every R, we want to define a space of CR, which is sitting between C0 and LA. So you should think of these as everywhere differentiable, like completely, sorry, not everywhere differentiable, everywhere differentiable of course, but differentiable of all orders. Whereas these are only differentiable up to order R. What this will mean is roughly that there's a Taylor expansion up to, with R Taylor coefficients, but after that there's some error term, and the error term rapidly vanishes. Okay, so these are these CR functions. But the slight subtlety is, unlike real analysis, you may have, and this can be done in the tutorial, you may have some functions which have derivatives of all order, but they're not, for example, C2. Okay, so it's not, your intuition is not, you should be a little careful. So there's a formal definition, you just sort of, I'll write it down in a second. Formal definition is, so if you have something which is CR or C2, then it has derivatives of order 0, 1, 2. The derivatives are continuous, but the converse is not true, not for example in Mumbai. Whereas in real analysis, both of the things are true in both directions. So this space CR, what is it? Yeah, so as I said, all the fuss, and there's infinitely many R's, so we have infinitely many Banach spaces there between LA and C0. And each one has its own flavor, and believe it or not, these things are useful in the study of modular forms. R is k minus 2. I should take R by 2 and R is k minus 2. So for all of you, I have to say that maybe right at the beginning that anything I do in my life has to be connected to modular forms, otherwise I don't do it. So it may go off in a big tangent into some other world, but ultimately there should, in the back of my mind, is always an application of modular forms. And Shaunak is happy because he will talk about modular forms. So, no, I mean, the thing is to somehow study the Galois representations attached to modular forms of type gamma naught p. what the structure of those representations is not be. Okay, so let's move straight to section 5, which is functions of class CR. Okay, so psychologically it takes a little time to even understand that there is a notion of derivative of a p-adic function on CP, right? You might think there's some really fancy definition of derivative, but it's not. It's just the same definition as in classical calculus. So definition, there is a popular book in Europe, but not so well known in India, a book by Shikov. I think he's Dutch. I think there's some notes of his floating around for many years. People have them, but I think it's also a published book. So many of these things are explained very well in a couple of his books. Actually, there's many papers and books on differentiability, continuity, class CR, etc. So we say that a function g from Zp to E is differentiable at x naught belonging to E if quantity g of x naught plus h minus g of x naught over h admits a limit as h tends to 0. Okay, so exactly the same definition of derivative. And all this makes sense, right? Because you can divide, I will subtract p-adic numbers, you can divide right in the field, and you can take limits, right? This is p-adic topology, so all of these make sense. So you just, if this limit exists, then if it exists, the limit is called g prime of x naught. Okay, now let me read out the next few definitions because they're all very obvious. You say it's differentiable of order 1 if g is differentiable at each point. Okay, so order 1 differentiable means it's differentiable at every point. Such a function is continuous, that's a little check. And you say it's derivative of order k if it's differentiable of order k minus 1, we define it recursively, and gk minus 1 is differentiable of order 1, right? So you denote the first derivative by g1, and you keep recursively defining the derivatives using the previous derivatives. You differentiate next time, then you say it's differentiable of order 2, etc. Same thing as in usual calculus. Okay, so now let's write down the definition of CR formally. So let R be a real number greater than or equal to 0. Say that G, let us say, I'm talking the words, let us say a function from Z to B, E is of class CR if there exist functions Gj from Zp to E for 0 less than or equal to j less than the floor of R, it's an integer, such that if you define epsilon gr, so this is the error term in the Taylor expansion, from Zp cross Zp to E by two p-adic things. So it's just the error in the Taylor expansion. So g of x plus y minus the sum from j equals 0 to r gj of x divided by j factorial y to the j. So that difference, the difference between the full Taylor expansion and the partial Taylor expansion, right? But there may not be any full Taylor expansion, so that's gx plus y. It may not have a full Taylor expansion. We don't know its local energy. So you look at this quantity and formally you subtract off something which looks like a Taylor expansion. So if this is the definition of epsilon, and one more quantity I need, which is called CGR from N or union infinity. So what is this? So is given by CGR of H. H is a natural number. It's the infimum of the valuations of epsilon G R X Y minus HR, where X belongs to ZP and Y belongs to P. So X is arbitrary, but Y is in a small ball, H ball around. I mean, Y is a small quantity, epsilon. Right? Y is like H over there. So, yeah, the infima, if this is CGR, then the error term, this is the valuations of the error, but there's an HR here. So if R is equal to 0, it looks more natural, but we're putting an HR there, we're subtracting off HR. So they're all if statements. Then, so it's CR if the following condition holds, CGR of H tends to infinity, or tends to 0, tends to infinity because it's the valuation tends to infinity, as H tends to infinity. So it's a little bit technical, but this is the formal definition of CR, which I wanted to put on the board so there's no, everything is defined properly. So again, epsilon GR is the difference between G of X plus Y and that sum. For each X and Y, X arbitrary, but Y belonging to a small ball, right? You look at this difference, the valuations of all these quantities, minus HR. Then this number depends on H. For each fixed H, H is fixed in this equation. Right? That's CGR of H. As you vary H, as H becomes 1, 2, 3, 4, 5, this number goes up to infinity. So the tails are getting very large in valuation. In norm, they're going to 0. But there's a minus HR there. I think it doesn't matter whether you put the HR in the infimum or outside the infimum, right? Because minimum is commutes with minus sign. So that's why it's a bit ambiguous in Kolmaz. And it also makes it a bit scary when you're reading it, but it doesn't matter. Okay, so great. So that's the definition of CR formally. Now, a warning is that, okay, so now there's some obvious remarks which I won't maybe carry out here. It turns out that this function G upper 0 is always just the G function itself, which you might expect. Some other remarks is that if you're CR, then your function has to be continuous. Every CR function is C0. That follows from this definition. You can try and manipulate that a little bit. Another remark is, okay, there are a bunch of remarks about uniform continuity, etc., but let me skip them. They're all done on page 26 of my notes. Okay, so this is just a space of functions. It's clearly additive, so it's going to be a vector space, etc. But why is it a Banach space? You have to define a norm or evaluation. So denote BCR, B prime CR, or G, or define, not denote, by the infimum of, it's a double infimum. One thing I've learned from this subject is everything looks very complicated, but you just take the minimum of everything possible on that page. Right? So whenever there's a complicated formula and you want to define a norm, you just take minimum of everything, that's going to be the definition. At the beginning it looks really scary, but so it's an infimum of the valuations of GJX over J factorial. So 0 less than equal to J less than equal to floor of R, X belongs to ZP, you take the infimum of everything like that. and also the infinimum of the epsilon terms. X belonging to ZP, Y belonging to P to the 8 ZP. The valuation of G epsilon, G, R, X, Y, minus R times dpy. Okay, this time I'm putting it inside because it depends on what.
Sir, in
Yeah.
this definition, Y is inside GP.
Oh, why is it CP? You're right, because
No, X
yes,
will
why is it CP? You're right. Why is that?
It's no H right in there, so
There is no H in here, that's true. There's no H. This is the H, VP of Y is the H. Right, so you have this slightly complicated definition. It's the minimum of two things. Each one itself is kind of an infimum. So that apparently is a valuation, and it makes CR into CRZPE into A and Ibana. Okay, so there's some. So this is just the existence of some functions like this, but they're not technically the derivatives yet, right? So if you CR, they just have to exist some functions. So what the next lemma says that in fact these are the derivatives. Okay, so I won't write that down. But when you first read this, you just think of these as the derivatives anyway, but they're not derivatives yet. But first you have to show that derivatives exist up to some point, and that these GJ functions are indeed the derivatives. Okay, so that's one proposition. Still on pages 27 and 28 in the notes. The notes go to about page 32, so I'm getting there. My timer is going off, saying I have very little time left. Let's stop it. There's another, yes. There's a formal theorem, a proposition actually, which looks so obvious. It says that locally analytic functions are CR. If you have something with Taylor expansions everywhere, and you parse series expansions everywhere, then there are times differentiable in this sense. Not R times differentiable, I shouldn't say that, it's not equivalent to that. But this definition of CR, yeah. So there's a proposition 5.7 which says, we write it here, section 3, I skipped a few sections, but locally analytic functions there's an H here, but it's true for all H, so you can just write. For any R greater than or equal to 0, the locally analytic functions are always of type CR. I already wrote that on the board. The proof is given in the notes on page 29 and 30. It's kind of fun to actually check some of these things. One has lots of hints, but it's a bit terse. So anyway, the proofs are more or less complete. Proof of that is there. Right. Now let me state a very important, one or two very important results. Okay, I might go 5 minutes over time. Because I'm going fast. Yeah. So there's a very interesting example, as I already mentioned. This is not equivalent to being differentiable of order R with inverse derivatives to R. It's a little bit different. One is as an example of a slightly weird function, p-adic function, which is differentiable everywhere. First derivative is 0, second derivative is therefore 0 also. Therefore all derivatives are 0 except for the, and that function is not of type C2. So maybe that can be done in the tutorials. Okay? So it's important to just work with that particular definition and not with anything else, not with any intuition. Okay, I'm going to section 4 now of chapter 5, which is at 5. So this is called amplitude coefficients of locally polynomial functions. Let me skip some notation and define the. Okay, let me not even talk about that. Let me go straight to section 5 and mention some important fact. So this is proposition 5.13, which is used very heavily in CG, in the paper I mentioned at the beginning of the 1.5 hours. So it says that if R is greater than or equal to 0, and G is CR plus CR, then, one more definition, and GH is given by the following formula. Sum I is equal to 0 to p-adic minus 1. Indicator function of the ball, I plus p to the h cp of x times a polynomial remember the derivatives exist. These functions are the derivatives or just the function, the definition of CR, the G uppercase, and it's a polynomial, so these are constants. So let's define GH like this. So on each ball, it's given by a polynomial, which looks like usual kind of Taylor expansion kind of thing. So this is the definition of GH. Then for this, the following hold. I won't write the first addition now. If R greater than 0, G belongs to CR and GH is that, then GH converges to G in CR in that metric. Okay, so these are some kind of, not really step functions, they're locally polynomial functions. Okay, they're almost step functions, but they're not quite. So on each ball, you have a polynomial, right? And these kinds of functions, as you take h larger and larger, they approximate G, the original function, in CRZPE. So this is something I'm going to use very, very heavily in lecture 4, that you can actually approximate these R times differentiable function, but not quite, by these locally polynomial functions. Okay, so that's one result I need. The proof again worked out very carefully in the notes. You can take a look. And I think that brings me to the last page. So let me just take the final theorem. So let me write down some. Okay, let me do two more results. Sorry, I'll be done on this board, I hope. You might wonder if there's an ONB here. There's no ONB given for CR. So research problem, or any of you who want to do p-adic functional analysis, find an ONB for CR. So really problem just occurred to my head, but it's not there. So he only gives a Banach basis. This is theorem 5.14. So what is the Banach basis of CR? It doesn't give an ONB. But there is an ONB if he is discrete by that theorem. And the value group is, I guess, the same as, yeah. That's not an issue. Let me define these EIKRs. So for I belonging to French natural numbers, and k belonging to French natural numbers, equal to 0, we set EIKR to be, again this is number theory, L of I, oh I didn't define L of I R, it the second, 1 of I plus p to the L of I, these are these wave functions, Cp of x times x minus I over p to the h to the k. L of I is a natural number n. It's the smallest n such that p to the n is bigger than I. Okay, I won't write it down. It's basically the p-adic logarithm of I plus 1. Okay, so L of I is the p-adic logarithm of I. It's the smallest natural number n such that p of n is strictly bigger than I. Anyway, so that's that. So this is a very, very precise kind of result. I mean, not result here, definition. You have some balls here, a polynomial on the ball, and you have some fudge factor, power of p in front of it. And there's a theorem of Gomez, not Gomez, but in Gomez, saying that the family of EIKR is the Banach basis.
I mean that p to the h should be p to the li?
P to the h should be, yeah, there's no h, so let's see what that is. P to the li, thank you. Then EIKR, R is fixed, I don't know why, principal notation. EIKR form a Banach basis. So this is only for K up to the floor of R. Form a Banach basis of CRCP. Okay, so that's I'm not going to use this, but maybe some extra cultural knowledge that you can write down a fairly explicit, quite explicit, Banach basis at least of CRCP. That's one theorem, and finally the last theorem, which is theorem 5.17. So say R is greater than or equal to 0. I'll explain it a bit more once I write it. And G belongs to CRZPE. And suppose G is given by a Mahler expansion, A and G, X choose N. Remember CR is of type C0, so I didn't prove it, but I mentioned that everything that's in CR is differentiable, should be continuous. So it has a Mahler expansion in terms of these binomial polynomials. Then the following quantity goes to infinity, the valuation of the A and G's minus R times the L of N. L of N is the periodic log of N. Goes to infinity as N tends to infinity. If R is 0, this is a familiar fact, right? If R is 0, this is just C0, right? And we need the norms of the valuations to go to 0. So these are going fast. If R is 0, this term is not there, and these valuations are going to infinity, and the norms are going to 0, right? But this is saying something a bit stronger than the valuations going to infinity. A valuation minus something is pulling it back. There's like trying to run a marathon up a hill, and there's a 10 kg thing on your chain on your right leg. You're pulling that along with you. So you've got to do a bit more work to go to infinity, right? So if a stronger condition holds, which you might expect because you want to be differentiable also, so this is a nice result. And you can then define a new valuation on CR, because these are going to infinity, you can define the, remember I put a prime in the valuation on CR before, B prime, you might have wondered why am I calling it a prime-adic valuation. Now the real valuation, which finally gets to at the end, is the minimum of all these quantities. So let be BCR without the prime, or G be the infimum of all these things. So to infinity, so the minimum quantity exists, right? Infimum exists. It turns out that this valuation and that valuation are equivalent And so you get the following corollary, which I'll write over here. P to the R log of n times x choose n is a Banach basis, a BB, which for me by now means bathroom break, the Banach basis of CR CPE. Okay, so each time you have to sort of modify the binomial coefficients with some condition in front so that get a new orthonormal basis of the smaller subspace. These are remarkably precise statements. It's actually telling you exactly what the Banach basis is, what part of P to put in front to make this a Banach basis. This looks a little weird, but intuitively you should be thinking, the final remark, C0. So suppose G is summation A n q to the n, or not q to the n, other forms x choose n, right? So C0 means that the ANs tend to 0 in norm, and CR generalizes this. That condition, if you just convert it to norms, it almost, in your head you can do it, but there's some subtleties with the floor and things. But it's saying that n to the R, AN is going to 0. So not just the AN is going to 0, but you're multiplying by a huge quantity n to the R, it's still going to 0. So much stronger than AN going to 0. So that condition over there translates into this condition, which takes a little bit of work to work out precisely, but it's more or less intuitively clear. Just stare at that. So it's a bit strange because Boy's papers have this kind of condition everywhere, and Colmay's always works with the original definition. But if you hunt 30 pages into Colmay's notes, you see their equivalent because of this theorem, this corollary. Okay, so that's all I want to say for now. I'll just say one more thing. It turns out that the Banach space is basically CR by 2 functions on CP modulo some log functions. Okay, so I wanted to make this a sort of high school kind of course. So next time we'll talk about p-adic log function and why it's CR. Like z to the n log z turns out to be CR for n up to, for r up to n minus 1. So you can differentiate it n minus 1 times 1 on the n time. So we talk about those kinds of functions. So Roy says you take all CR by 2 functions and you divide by some sort of log function, sums of log functions. And that's the Banach space. So it really is high school definition using the digital differentiability. Nothing fancy involved in the Langlands correspondence. That's the Banach space BKL. So we'll do that in lecture 3. Okay, so this was the sort of a background to that. Any quick questions?